of the solvent for dissolving. One is the solvent solubility, dispersion, solubility parameter of solvent, the polymer, solvent, polymer. Therefore, we have different properties of the solvent polymer. We calculate this RA, obtain a number, an amount, okay? And we have the solubility, we have this RA0 is solventation radius. R is radius. Solventation radius of an polymer. For example, for polysulfone PVDF, we have this number. Okay? We have this number for polymer, for example, is 10. We calculate RA for our solvent and PVDF. If we obtain 12, this 10, this 12. Red will be 12 per 10 will be 1.2, okay? Red, if red lower than 1, solvent can dissolve. When we obtain 1.2, we say that our solvent cannot dissolve because red is larger than 1. But if we change the solvent, we obtain RA as 0.8. 8. We obtain 8, and this is 10. Therefore, red will be 0.8, and we say that this solvent can be dissolved. Therefore, this equation, with having of this equation, we can calculate the possibility of dissolving a solvent for a polymer. This diagram shows, I say that this R is a radius. This R0 is radius of a polymer. If our calculation located inside of this sphere, we say that the solvent is good and can dissolve. If red is larger than 1, that means the out of this sphere, therefore bad solvent and cannot dissolve. Most of this sigma these sigma parameters, they are in tables. They are in handbook. You can find these amounts, sigma D, sigma P, sigma H, for DMAC, DMSO, NMP, in the handbooks, in the tables. For polymer also, okay? But you synthesize it a new solvent. And you check the handbooks, and you do not find. In this case, we can calculate these sigmas with this equation and with this functional group. There are, you see, for example, in this FD1, and with base of the structure, we draw the structure of a solvent, and based on the structure, we can calculate these amounts and the next use in the Hansen solubility parameters. Every functional groups have a specific amount, and with using of this amount in these equations, we can calculate the Hansen solubility parameter. V is the volume, molar volume of the groups, and this F is the located the amounts here. Therefore, if we have a new solvent that no data in the literature. With using of these equations, we can calculate the sigmas and go back to this equation. We calculate the RA and the R0, and we can predict that this solvent can dissolve or not. For obtaining, if we have a new biopolymer, for the first time we synthesized a new biopolymer, our new polymer, we need to calculate also R0. For famous polymers, there is R0 result in the literature, but for new polymers, there is an equation. We must use 22 solvents for dissolving this polymer. And we say that this polymer, we select 22 solvents. We say that our polymer dissolve in chloroform very high, 2+, in DMAC good plus, in the water no minus. We have a table plus, 2+, minus. And based on this 22 solvent, we can calculate this RA0. Now we go to the examples. If any question about Hansen solubility and as a high green solvents, the water is the best one. If we can prepare the membranes with water, it is better. But we know that the water is very polar and only can dissolve the hydrophilic, very, very hydrophilic polymers. Therefore, only these polymers can be used in fabrication of membranes with water as a solvent. You see that the famous one is PVA, and this right is the natural polymers, biopolymers. And if we prepare, for example, chitosan membranes, both polymer is green and solvent is green, and is very good. But most of these polymers, when is soluble in water, during the using of membranes, the water can be dissolved the membrane. And after 2 days, the membrane will be destroyed. Therefore, for removing of the solubility, we must change thermoplastic polymer to thermoset. We have two types of polymer, thermoplastic, thermoset. Thermoplastic can be dissolved in solvent, thermoset cannot. Thermoset, that means we have a cross-linking between the chains. Solvents go for separate, but cross-link do not permit. Therefore, in the fabrication of the water-soluble membranes, we must use cross-linking agent for removing of the solubility. Therefore, in this all of mixture of in these solvents, water and these polymers, we add the third section, mostly glutaraldehyde as a cross-linker, that during the curing of membrane, during the cross-linking, the solubility of the membranes will be removed. So PVA, previously we discussed, PVA membranes can be used in pervaporation. In pervaporation, we say that if we want to separate water, low amount of water, from an organic solvent, we use PVA, and the membrane type is non-porous. Therefore, the fabrication of the pervaporation membrane with PVA is easy, and there are commercial PVA per evaporation modules that is very green, and we have a water solvent. For grafting of these groups on the membrane surface, we also can dissolve these polymers in water and use for grafting, or we can fabricate the membranes with chitosan, xanthan gum, dextran, and carboxymethylcellulose. CMC is carboxymethylcellulose for production of the membranes. Both porous and non-porous membranes can be prepared. In this case, we have not used water as non-solvent, because here we have a water as a solvent. Therefore, for example, for production of the non-porous membrane, we used WIPS method. We dissolved the PVA in water, add crosslinker, coat on the glass, and with heating, we remove the water. And when water go to the atmosphere, we have no problems. But in the traditional solvents, when the acetone go to the weather, cause to the ozone layer problems and others. With additional pore-former, we can porous this layer with addition of pore-former. As discussed in membrane distillation, we say that we have a low critical solution temperature. That means in high temperature, polymer is dissolved, and when reduce the temperature, polymer is insoluble. High temperature soluble with reducing, and we say that it's thermal induced method, TIPS. In the TIPS, in high temperature, we dissolve the polymer. With reducing of temperature, solubility is removed and phase inversion happens. In this example published in this paper, used the polymer, you see that can dissolve in the low temperature, and with increasing of the temperature and evaporation, we have a membrane, and next by reducing and solidification for removal of the membrane, we can cause it in the water bath. Therefore, there are many different techniques for fabrication of the membranes with water as a solvent. Or we have a polyelectrolyte. The soluble polymers in water is named polyelectrolyte, the soluble polymer. Polyelectrolyte or polyelectrolyte are soluble polymers in water that can be cationic or anionic based on the functional group. With change of the pH, you see here, we want prepare a membranes from water-soluble polymers. Polyelectrolytes are soluble in water. Okay? For fabricating of the membranes from polyelectrolyte, we mix two polymers, one with negative charge and one with positive charge. Okay? We dissolve the polyelectrolyte. This polyelectrolyte mostly used in coagulation process in the water treatment for increasing the precipitation of the iron or aluminum in the coagulation bath in wastewater. We add one positive polyelectrolyte and one negative polyelectrolyte. And we have a solution. But by change of the pH, we reach to a point that the amount of negative and positive charge is equal in a special pH. In this case, we have this arrangement. The negative charge contact the positive charge. Okay? Understand me? And when reach together, contact together, and the solubility removes and precipitate. And phase inversion happen. Phase inversion is the separation of the solid from the liquid. With a specific pH, the positive and negative charge connect, attach together, and precipitate. And for example, in this case, in high pH, we have a soluble polymers. In a low pH, we have a not soluble polymers, and we can prepare porous membranes from the polyelectrolyte and from the water as a solvent. This is a very good technique for fabrication of polymeric membranes with use of water as a solvent. And fabricated, you see the high porous membranes with this technique. After water, if we can use bio-based solvents, is very good because we produce this biosource from the bio-based, from fats or oils, or from the herbals, okay? Therefore, if we can produce these solvents from the biomass or from the fats and oils, the toxicity of this solvent is very low and biodegradable, and after use, the release to the environment is not a problem. There are different categories. The famous one in the membrane fabrication, this is one. Some examples. The famous bio-based solvent is ethanol. Ethanol produced from sugar. And therefore, it is very, very green and no problem of use. Therefore, but ethanol, such as water, is a polar and hydrophilic solvent and can only dissolve the soluble, the hydrophilic polymers. Some polyurethane, some polyvinyl butyral, PVA, polyethylene glycol can be dissolved in ethanol, and we can use ethanol for fabrication of these membranes as a nanofiber or as a flat sheet and others. PEBOX is a famous polymer in the fabrication of gas separation membranes, and more than 30 or 40 years is used for the fabrication of commercial carbon dioxide separation membrane, and the solvent of PEBOX is ethanol. And industrial scale, ethanol is used for the PEBOX dissolving for fabrication of RO membrane. The bio-based solvent is silane also. Silane, this is an NMP, traditional one. This is the structure of the siren. And you see that there are some similarity between them. And in most cases, siren is used instead of NMP. And see that with use of the siren and control of conditions, we can dissolve PVDF and polyethyl sulfone, and the good membranes have been fabricated. I have some studies about use of green solvents in the membrane fabrication. The membrane is good, the flux good, but the stability is low. In the papers, maybe do not mention, because everybody wants to say that our membrane is good, but our results show that when we use bio-based, for example, this siren, the resulted membrane have 50% lower tensile. The membrane prepared for NMP is very stable, no tear, but the membrane fabricated with siren, with applying stretch, it spear very easily. Therefore, the polymer siren can be dissolved, first dissolve, and second, we can produce the membrane. But the strength of the membranes is low and the tensile is low. Valerolactone, you see the similar structure to the NMP, and also used in the fabrication of the membranes. For fabrication of this valerolactone, this biomaterial is used, levulinic acid, separate from the oil, vegetable oils. The methyl isosorbate with this structure also is used in the fabrication of the membranes. Therefore, we can use the bio-based membranes for bio-based solvents for the fabrication of the membranes. The third group is green synthetic solvents. Green synthetic. That means that these solvents chemically synthesized, not in the bio-based, but the fabrication method and the properties of the solvent is green, and most of these solvents you see have a carbonate base. This is organic carbonates. This is organic groups. Most of these categories have this structure, and with change of this R1 and R2, we can change the solvent properties for dissolving our polymers. For example, this is the solvents used for dissolving these polymers, that's polyethyl sulfone, polysulfone, polyacrylonitrile, and others in this study, and shows that we can use most of these solvents in the fabrication of MF, UF, and NF membranes. With change of the solvents, this study shows that prepare the NF, UF, and MF membranes with polyethyl sulfone, PVDF, polysulfone, polyacrylonitrile, and obtained these membranes. The most famous green synthetic solvent is DMSO. DMSO traditionally is used in the membrane fabrication and have a similar behavior as DMAC, DMSO. The obtained solution is relatively high viscosity, and we can use this for fabrication of membranes. We have another green synthetic solvent as a Tommy solve. This is an NMP, you see, and this is the similar NMP, only have 3 extra aliphatic group. The microorganisms mostly cannot be eat the cyclic materials or aromatic materials. Aromatics and cyclics are toxic for microorganisms. When we have this compound, this structure in the membrane, in the organic compounds, in the biodegradation, the bacteria cannot eat this one, but easily can eat the aliphatic. Most of the oils, fats, have this structure. And this fatty acids very easily eat with bacteria. In this case, this is a toxic, but this is not toxic, because these groups help the biodegradability of this solvent. Therefore, with a little change in the NMP structure and change it to the Tommy solve, we can increase the greener behavior of the solvents, and the microorganism can biodegrade these solvents. And this study shows that the Tommy solve can be replaced with NMP, and we can use these solvents for fabrication of membranes, but the price of Tommy solve 5 times bigger than the NMP. Why? Why expensive? Because low production. Because low production. Both the solvents is synthetic, but it is very usual from 100 years is used, but this is the new one. After 10 years, I think the price of these solvents should be similar, because we go to the greener solvents, and we're forced to use these solvents. Therefore, production of the green solvents will be increased and the price will be reduced. Another very green solvent is ionic liquids. Ionic liquids, mixture of 2 organic compounds, or 1 organic, 1 inorganic compounds. Then when we mix these 2 cation and anions together, we have a liquid. And this liquid can act as a traditional liquid, but very environmental friendly. Ionic liquids have not volatility, no vapor, and very good low vapor pressure, but very expensive now, very expensive. But the studies shows that we can dissolve some polymers in this ionic liquid, and we have many thousand ionic liquid with mixing different cations and different anions. Therefore, there are many ionic liquids, and we change the properties of the solvent with change of this group. We can have hydrophilic solvent or hydrophobic solvent, polar solvent, non-polar solvent. In this study, use the cellulose and this type of ionic liquids for dissolving of the polymers and fabricated hollow fiber membranes. Or in this study, dissolved PVDF HFP in this ionic liquid and fabricated the different morphology of the membranes. We have a software as LCA, life cycle assessment. That is very important that we calculate and see the different aspects of a process for production of a product, okay? With calculation of life cycle assessment, we see that our suggested compound or product, how can influence in different aspects of the environment. These compounds, how affect in the weather, how affect in the water, how affect in the soil, and others. So there are many, for example, eutrophication potential, how affect in the growth of the microorganism in eutrophication process. Human toxicity. This compound is toxic for human, toxic for vegetables. Photochemical ozone accretion potential, aquatic, very, very different, more than 20, 30. And in this assessment, we have a Simaporoma software. Name of software is Simaporoma. That assessment the life cycle. In this study, investigated the use of this ionic liquid and compared it with toluene and see that the ionic liquid is very good for environmental, but in this aspect, toluene is very bad. Therefore, if we replace this ionic liquid with toluene, very good for environmental aspect. And the final categories of the solvent that now is very important, this is the new solvents, is deep eutectic solvents. Deep eutectic solvent is similar to the ionic liquid solvents, but is very, very cheap. And fabricated, for example, from urea, glycerol. Oh. Urea is solid. Urea is solid. This compound is also solid. Oh. We have a donor and acceptor. Hydrogen bonding, like hydrogen bond acceptor, hydrogen bond donor. One give, okay? When we mix one HPA with one HPD, they contact together and mixing and reaching to a point that this point is named eutectic point, deep eutectic point, okay? We have also peak eutectic oid. Why say deep? Because in this dip, with the mixing compounds, we go to the peak eutectic. That we see, this is the temperature, that we see that, for example, this chlorine mixed with the urine, okay? Both is solid. And when mixed to white solids and mixed, after 10 minutes, we have a liquid. We produced a liquid, a solvent from two solid with mixing. This is 100, this is 15. With mixing, we go to the 10 centigrade, and we have a liquid. And this is liquid, is cheap, because they used materials, glycerol, ethylene glycol, urea is very cheap. And therefore, if we can dissolve the polymer in these diputectic solvents, we can prepare a green membranes. And these materials are not toxic. Urea are not toxic. Glycerin are not toxic. We use glycerin every day for our skins. Therefore, in diputectic solvent, we have a donor and an acceptor, and we can mix with different ratio. 1, 1, 1, 1, 1 mole urea, 1 mole chlorine. Or 2, 1, 3, 1 with different ratio, and we obtain different properties solvents, and we can use this in the membrane fabrication. The experiments showed in this study can fabricate PVDF membrane with this. Use 3 different this 1, this 2, and show that we can dissolve the PVDF and obtain the different morphology and different pore size. It is very important. Now my 2 PhD students work in this area, and we published a review paper in 2021 about the use of this solvents, as it is a very important aspect, and in the future have a very good progress in this process. This is our calculation. We have another review. We suggest that which solvents can be used in the membrane fabrication. And in this table, we suggest for the first time that this can be used in the membrane fabrication with polysulfone, polyethyl sulfone. And we calculate Hansen solubility, and shows, we say that the red RED is lower than 1, can dissolve the polymer. And we suggested that these solvents can be used in the fabrication of these membranes, and have a good citation, this paper, because based on this table, they select our suggested solvent and fabricate the membrane and say that we selected this solvent based on this table. There are some challenges with this green solvent. One challenge is the suitable viscosity. Usually, the bio-based solvents have very, very high viscosity. In use of NMP, DMAC, traditional solvents, we prepare 20% polymer solution. That means we add 20 gram polymers to 80 gram solvents and prepare a good solution with good viscosity. But when we use the green solvent and we add 20 gram to 8 gram solvents, we have very high viscous solution, and we have to reduce the concentration of polymers. And when we reduce the concentration of polymers, we have a big pores. We want to prepare nanofiltration membrane, but because we reduce the polymer concentration, we have a microfiltration membrane. Therefore, one of the problems it is high viscosity. And when we use the low polymer concentration, our resulted membrane is very porous. And when it is very porous, the stability, durability is low. And the mechanical strength is reduced. In most cases, for dissolving of a polymer in the green solvent, we must use high temperature. in 25 in the air temperature, the polymer cannot dissolve. Therefore, we must reduce to 90, 100 centigrades and cast the high temperature. This is the second problem from industrial application and energy consumption. We have not uniform film. When we cast, in some cases, we have a not good film. We have a good solution. We have a good soluble, but give not good film. And we have not prepared a good film. In most cases, in the NIPS method, when we use NMP, dematch, and non-solvent is water, dematch with water is miscible. Miscible that when we add them, no two phase, one phase, okay? But in bio-based green solvents, because bio-based and such as oil, therefore no miscible with water. And when no miscible, do not want to go to the water. And we have not phase inversion. We prepare the film, go to the water. But bio-based solvent do not go to the water, and we have not good film. Okay, some problem. High price is very important. Our most ionic liquids and this have very low volatile, and the WIPs and EPs for fabrication of the dense membranes in, for example, protein exchange membrane, we cannot use because they are not volatile and not vapor. And therefore, we cannot prepare a dense films. The researchers are in this area focuses and suggest new green solvent, diputectic solvent, ionic liquids for dissolve these talents. High price, this shows that the price of these solvents usually 3 times more expensive, but I think that will be reduced. Low strength, I say that these membranes usually have a low strength. Time is finished. The second aspect is the biopolymer used. If we can use the biopolymers in the membrane fabrication, after 3 years, 4 years, 5 years that the membrane is destroyed, we can degrade these biopolymers with landfill and other methods. Therefore, it is better we use the natural resource polymers such as cellulose, cellulose acetate, starch, lignin, and others can be used. Usually, today's focused on the use of polylactic acid. Polylactic acid is very good biopolymer for production of the membranes, and now most researchers focused the use of this biopolymer in the fabrication of different type of the membranes. Thank you for your attention.
Any question from the audience side?
Sir, LCA cycle, life cycle assessment.
Yes.
Out of all those parameters, which one will give more emphasis to determine?
For LCA assessment, we must give some information to software, and after giving this data, the software will calculate based on our dictionary, the software, Simaproma software, and predict and say that this, for example, solvent, or this polymer, or this method, in all of them, from the economical view, how compare. You give some price of the materials, and mostly compare in the LCA, we compare 2, 3, 4 processes together, not one process. For example, you see, compare toluene with ionic liquid. In this case, say, based on our literature, our data. For obtaining this data, we usually use the other published literature, books, handbooks, Google's patents, and we, for example, we add boiling point of the solvents and other parameters, molecular weight of polymers, prices, and if there are some papers that reported the durability, stability, chemical resistance, and everything. Add, and after that, the software run and calculate different aspects of the your process or your component. Okay. Very interesting software.
What's the software name, sir?
Yeah.
What is the software name? Name.
Sima Proma.
Sima Proma.
Sir, like you mentioned that the eutectic solvents and ionic liquids, if they have high viscosity, you will get big pores, right?
Yes.
I have a doubt. We can actually tune the viscosity and polarity of these solvents synthetically.
Yes.
Then we can use, we can plan the desired polarity and viscosity. Like if we want small pore size, so the viscosity should be low.
Yeah.
So we can tune them synthetically. So is that applied? Is that mechanism applied in this membrane technology? That's the doubt I have.
Your question is the effect of viscosity on the membrane fabrication?
No, you already explained about the effect of viscosity on membrane, but I'm asking can't we tune them? Like if we tune them, the polarity and viscosity of deep eutectic solvents and ionic solvents to the desired ratio, and then we can utilize them.
Yes.
Is that possible?
Yes, it's possible. There are many cationic and anionic group in ionic liquids, and donor and acceptor groups in the deputective solvent. With change of these groups, we can arrange the polarity, hydrogen bond, and also we can change the viscosity. And we can manage both viscosity and polarity. But one big problem is the buying of the materials. When you want to change many functional groups, you need to buy 50 components and need the money. And therefore, these investigations needs very big grants and big projects. And usually in MSc or PhD thesis, we have not this money. And it is very good idea that we can manage functional group polarity and viscosity to give the better performance. In the most papers you see select 3, 4 days based on our calculation and published paper and investigate them. Therefore, most want to prepare a good membrane, not control the viscosity, but if possible, but need a very big project.
I just would like to add one more thing here, because when I was doing my PhD, one time I was working on a membrane with polyaniline, and where I already had a zinc chloride as an additive in the membrane. So what I was seeing is that my membrane was very spongy type, and the viscosity of the solution was very low. The membrane was having very spongy nature. So from a low filtration with just variation of polyaniline from 1 to 4%, the viscosity varied in such a way that it actually went from a non-Newtonian behavior of that casting solution to almost a Newtonian behavior, almost a straight line we obtained in a rheometer. And there was a huge variation in pore size with the influences the pore size or the pore distribution inside the membrane.
Yeah.
So there are a lot of studies going on, and there are huge scope of more
Yeah.
research.
Yes, yes, yes. Also, I say that with addition of some particles, some polymers, we can manage the viscosity. For example, we want to prepare microfiltration with big pore size. We want to have a low amount of polymers. For example, 6%. But in 6% PVDF in DMAC, the solution is very, very low viscose, and we cannot cast. In this case, add 10% polyethylene glycol. Polyethylene glycol is soluble in water. With addition of polyethylene glycol, the viscosity increase, we can cast, but during the phase inversion, the polyethylene glycol go to the water and also increase the porosity, and also we manage the viscosity. Some salts reduce the viscosity.
Thank you
Thank
very
you.
much for your insightful talk. And so now we will proceed for a small tea break.
Okay.
After that, in 15 minutes, we'll gather here in this room.
Thank you.